Alright, so where we last left off, we had this sort of potentially intimidating looking equation here. If this is a matrix A, and I don't know, some little vector equals some other vector, the idea is that in principle we're solving this like any algebra equation where we divide by A, except we can't divide matrices, but we do have inverses sometimes, and this one is invertible. So what we need to do is find the inverse of A and multiply it by C. Now I've already done this. So on my calculator, I have a matrix for A. Whoops. Show you it. And I've got those numbers in my matrix already. So all of these numbers are in my matrix, 3 by 3. I also have another matrix as a 3 by 1 with my initial condition. And so then I can take matrix A inverse times matrix, name C, and this will give me the answer. Now, I don't know if it's a funny story or not. Oh, I'll tell you in a second. So what does this equal? This equals 6.3, negative 10.86, and 41 point, I don't know, whatever, 1, 2. Definitely not worrying about sig figs here at the moment. Now the thing with these kind of problems is there's so much time spent. Keep in mind, we didn't actually find the eigenvalues by hand, or the eigenvectors by hand, or the inverse by hand. In some sense, this is as fast as this problem is going to go. So you get to a point like this, and you might wonder, what did I just find? So what did I just find? What are these A's? What are those A's? Ah, right. These are the unknown constants in the general solution. That's right. I'm finding a particular solution because I know the limit is going to be one of those constants times one of the eigenvectors. Oh, okay. All right. That makes sense. So then I can write down my solution. So my bare ground and grass and shrubs is going to be 6.3 times e to, whatever, some negative 0.5 t times an eigenvector minus 10.86 e to the minus 0.176 times v2. You can tell I don't care a whole lot about those things. 41.12 e negative, no e because this is just 0, right? Times v3. Now I do want to list out the eigenvectors here, and so I'm going to. This is 0.437, 0.752, 0.1315. So because I haven't asked anything about what happens in 3 years from now, I'm just interested in the limit. These don't matter because they're going to go away. So now we've got the form of the solution. Now we just have to put it together. So the limit as t goes to infinity is going to be this last term, 41.12, times these 3 components. And let's multiply them out and interpret them. Make sure they make sense. All right. So, make sure my little note sheet here. I wrote down those values wrong. Did I? I think the numbers are okay. 0.4. Oh, I goofed here. Maybe I might have goofed. I'm just going to have to shoot this again. Oh, I goofed in the way that I wrote it down, but I didn't goof in the way that I recorded it here. Let me pause this for a second and fix this matrix. Yeah, I wrote the transpose down very carelessly. I had written out my 3 eigenvectors I got from Wolfram, and then I proceeded to write my matrix in the same sense. The columns are supposed to be the eigenvectors, not the rows. So this right here is the correct matrix. Now everything else is fine because I had the correct matrix in my calculator. So if you need to see these, just pause this and look at it. Going back down here, however, this eigenvector is not correct. So this should be 0986, 090986, 01315, and we're going to multiply those three numbers by 41.212. So let's do that. And so we're going to get 41.12 times 0.986, and that gives me 40.5, say 4, and then we'll multiply by 0.986. That gives me 4.05, and then we'll multiply by this last number, 0.1315, and I get 5.4, And what is this? Well, this is what bare ground grows to. This is what grassy ground grows to. This is what shrubs grow to. And notice that these numbers, they add up. I think so. Yeah, right. I mean, 49, 9. Yeah. So they add up to 50. And they should add up to 50 or very close. Again, there are rounding errors here, so that can happen. So this is the limit. If you imagine playing this movie of bare ground, eventually, after infinite time, you've got something where about 80% of it, you started with 50, so you got most of it is still bare, obviously splotchy, and then you get a little bit more than half is shrubs, and then you get a little bit of grass. So not in this particular form, of course, but this is what happens eventually. Okay, so just a brief review. What did we do? Well, we started out modeling how bare ground is reclaimed by grasses and then shrubs. We made a set of differential equations, turned it into a matrix equation. We find the eigenvalues for it, consider the eigenvalues as possibly being artifacts of the numerical process, figured out what the limit ought to be, use the initial condition, which involves some more matrices. Then we ended up with our values for our unknown coefficients. Took our unknown coefficient that we wanted, multiplied by the last eigenvector, and then ended up with the long-term amounts of land starting from 50. That would be bare, grassy, or shrub.